In this video, we will talk about Gauss's law. Two main ingredients of Gauss's law are the electric flux, denoted like that, and the electric charge. So first, we shall look at the concept of electric flux, the definition of it, and also how to calculate electric flux. Then we will present Gauss's law, followed by a few solved problems based on these concepts. Before defining electric flux, we shall look at the concept of area vector. For a surface such as this one, a flat surface with surface area A meters squared. So how do we define an area vector for such a surface? Now we know area is a scalar. Area vector is defined in the following manner. The direction of area vector for a given surface such as this one is perpendicular or normal to the plane of that surface. So in this case, the yellow arrow here denotes the direction of the so-called area vector. The magnitude of this area vector is quite simply the surface area of that surface. So we can write the area vector for this particular surface in the following manner: the magnitude and the direction, n hat. So this is the normal vector to the surface. A normal unit vector, that is, a vector that is perpendicular to the surface with magnitude 1. Likewise, if you have a surface that looks like this, let's say the area is A1 meters squared, the normal vector to the surface is going like that. So that is the normal vector. It's perpendicular to the surface. And the areal vector for this surface, let's denote it as vector A1, is quite simply the magnitude of that surface area A1 times that normal vector n hat. As simple as that. What if the surface is a sphere, as shown here? Let's look at two areas, area 1 and area 2. So this surface right here has an area of dA1. Note that this green arrow represents the normal vector to this surface 1, and we shall denote that normal vector as r hat. Now why r hat? Because this normal vector is in a radial direction. So the normal vector to this surface 1 is a radial vector with magnitude 1. So the area vector for surface 1 can simply be written as follows, like that. Now likewise for surface 2 with area dA2, the normal vector is represented by this green arrow, and we know since this is a sphere, the direction of that normal vector is also radial, r hat. So the area vector dA2 can be written in a following manner, and just like that. Now we are ready to define electric flux. Now electric flux is defined in a following manner. It is a dot product of the electric field and the areal vector. So say that we have a surface, a flat surface like that, with area A meters squared. We already know that the normal vector is heading like that, n hat. Now let's assume you have electric field penetrating the surface area in that direction, like that. And this electric field makes a certain angle with the normal vector. Let's call that angle theta. So the electric flux through this surface due to that electric field can be written in a following manner. So it is just the magnitude of the electric field E times the area of that surface A times cosine theta. So this is just from the definition of dot product that we have introduced some time ago. An important thing to realize is that the unit for electric flux will be newtons meters squared per coulomb, and it is a scalar. Let's look at two special cases for electric flux. Assume that you have electric field in the direction parallel to the normal vector, namely, the direction of the electric field is perpendicular to the plane of that area. So that would make theta, the angle between E and n hat, to be 0. So in this case, the electric flux through this surface with area a meters squared due to that electric field is quite simply E times A, because cosine of 0 is 1. So we say the electric flux in this case is maximum. So whenever you have the electric field perpendicular to the plane of the area or parallel to the area vector, we say the flux, the electric flux due to that electric field through that area is maximum. The second case is when the electric field is going like that. It lies on the plane of that surface and therefore making 90-degree angle with respect to the area vector. In this case, since the theta is 90 degrees, we say the electric flux due to this electric field through that area is identically 0. Let's look at a general case. Let's assume that you have a sphere. So in this case, the surface is a closed surface. It is a sphere. And let's say you have electric field going radially everywhere, like that. So this surface, this sphere with radius r, has normal vector also pointing in a radial direction. Let's call it like that. Since the electric field now, although it may have the same magnitude at a fixed distance from the center, but the direction is now different, we should treat it as a non-uniform electric field, at least as far as the direction is concerned. So to calculate electric flux, for this case, what we have to do, we have to integrate that dot product that we introduced earlier, like that. And this will give you the electric field is radial. Let's assume the magnitude is E, but the direction is radial. Now, the elemental area vector for a sphere is also in a radial direction, so we can write that in the following manner. Now, dot product of two parallel vectors is 1, and this integral will simply become E dA. We will show how to use this result for some simple system in a few minutes. Now we are ready to define Gauss's law. Gauss's law is defined in the following manner. It says the electric flux through a closed surface S is equivalent to the amount of net charge that is contained within that closed surface S divided by a constant epsilon naught. This constant here has a value of 8.85 times 10 to the power minus 12 in the units of coulomb squared per Newton per meter squared. It's called the permittivity of vacuum. So what Gauss's law says is that if you have, let's say, an arbitrary closed surface, S, and you have electric fields going like that, the electric field may be non-uniform and acts in some complicated way. So the electric flux due to this electric field through the surface S is given by this expression. So that means it's directly dependent on the charge, the net charge that is contained within the surface S over epsilon naught. As an illustration, let's look at this closed surface S. Let's say initially you have one positive charge with magnitude, let's say 1 coulomb. So this positive charge would obviously create electric field like that. And if you ask what is the electric flux through this surface S due to that electric field, E. And the computation is simple. So the electric flux to that closed surface is quite simply the net charge is only 1 coulomb over epsilon naught in the unit of Newton per coulomb meter squared. Next, let's introduce a negative charge with the same magnitude, but now it's minus 1 coulomb. Now what is the net electric flux through this surface S? So it's 1 plus minus 1, and therefore the electric flux is quite simply 0 because the net charge within that surface is 0. And likewise, let's say you have a negative charge outside or positive charge outside with some strength, and it creates, of course, the electric field in a following manner, like that. Now, if we ask what is the electric flux through this surface S, immediately from Gauss's law, since there is no net charge in this region bounded by that closed surface, you can say that the net electric flux through that surface is identically 0. Due to the fact that this charge here, although it's present, but it's outside that surface. So within the surface, there is no charge or net charge. Let's look at the following simple exercise. Let's say you have a positive charge in the middle of this sphere, and the strength of this point charge is Q. The radius of the sphere is R. So obviously, this point charge will create electric field through this spherical surface in a radial manner. Calculate electric flux for this example. Now we know the electric field is radial, and it's given by KQ over R squared in a radial manner. Now dot it into smaller elemental area that forms that spherical surface, and that elemental area has a vector in a direction of radial as well. And since the field has different direction at different points, we end up integrating them. This expression, I mean. Now R dot R is 1, so you can take all the constants out. Note the field at the surface of the sphere is constant, namely KQ over R squared. So integrating dA, this is a spherical surface, you get KQ over R squared. The area of a sphere is 4 pi R squared. So R goes away, giving you 4 pi KQ. Now K is a constant, which we introduced when we discussed Coulomb's law. It is related to permittivity of vacuum in a following manner, 4 pi epsilon naught. Substituting this in here, you see the flux will simply becomes Q over epsilon naught, Q being the net charge within that surface. When defining Gauss's law, all these closed surfaces have a term or name for them. They are called Gaussian surface. So in this example, the Gaussian surface is this spherical surface. Let's look at the following problem. A point charge 2 nanocoulomb is at the center of a cube with sides 0.2 meter. Find the electric flux through one of the 6 faces of the cube. Of course, being a point charge, the direction of the electric field is going to go like that. So how do we determine the electric flux? The total electric flux through this cubical surface is the net charge, which is 2 times 10 to the power minus 9 coulomb, because it's given as nanocoulomb, over epsilon naught. Now we know epsilon naught is 8.85 times 10 to the power minus 12 in SI unit. We're interested in electric flux through one of the surfaces. So there are 6 of them. So all you have to do is take this result and divide that by 6. So 2 times 10 to the power minus 9 over epsilon naught. And that will give you 37.7 newtons per coulomb meter squared. That solves the problem. Thank you for watching.